Okay, welcome to lecture 11a, Reynolds transport theorem and continuity. What I want to mostly put out there today with these objectives is this first one, understand the control volume approach. Everything else is secondary to this. So probably in the A portion of this, we're going to work on these two. We're going to develop the continuity equation from the Reynolds transport theorem, which of course you've never seen before. At least I'm assuming that you haven't. And then we're going to solve problems using continuity, and that'll be in the B section. But through the whole thing, really, this first one is the one I care about, understanding control volume approach. Continuity equation is going to be one of the tools that we use basically constantly as we move through the semester. So be prepared for that because it's going to happen. So I'm going to start here with the Reynolds transport theorem. And so here's the Reynolds transport theorem, and we're going to look at it and, Reynolds transport theorem. Okay, so if we zoom in here, you can see probably one of the most complicated differential equations that you guys have ever seen. I recommend pausing it and copying it down because we're going to talk about this for a little bit. Okay, so what we're going to do here is what we're looking at is B, okay, this capital B. And this is some property of the system, of a closed system. Okay, and then lowercase b is that same property per unit mass. Okay, so it's B per unit mass. All right, so I'm going to kind of walk you through these terms one at a time. Okay, so we take this first term right here. Okay, so this is the rate at which this capital B, okay, accumulates. So it can be positive or negative. So it could be a negative accumulates in the system. Okay. And then this one right here is much more complicated. Okay, because this one, let's see. Let's try to think about how this is, because I'm not just going to tell you this. I want you to think about this. Okay, so B is something per unit mass. So let's suppose capital B is momentum. No, let's not make it momentum. Let's make it salt or something. Okay, so this is salt in the system. So capital B is salt. Okay, so lowercase b is salt per unit mass. Okay, so maybe it's salt per kilogram of salt water or something. All right, so if we multiply that by the density, which is mass per volume, okay, mass per volume, right, then I'm getting, these masses are going to cancel out. I'm going to get salt per volume. Okay? Now, what I'm going to do then is I got salt per volume, but then I'm going to multiply it by a little integral dV. Okay, so basically I'm going to multiply it by a volume for a tiny little section. So I got a tiny little section of something. And I'm going to multiply it by this volume, this tiny volume. But then I'm going to integrate over my entire control volume. Okay, so basically I'm adding up all of these little volumes. Okay, I'm not really, in each of those volumes basically, so I'm taking this little volume right here. I'm going to multiply it times this salt per volume. So basically I'm going to get the salt, the total amount of salt that's in one of these tiny little volumes. Okay, and then I'm going to add them all up over the entire control volume. So I'm going to get the total amount of salt in, okay, I guess it's the total salt in the control volume. Okay, and then I'm going to do d by dt. So I'm going to say that means I'm taking the derivative with respect to time. So I'm saying, how is the total amount of salt in the control volume changing in time? Okay, if it were salt, of course, but it's actually lowercase b. So I could say this is the rate at which uppercase B, so that's salt in this case, in this example, accumulates. Again, it could be positive or negative. in the control volume. Okay, so what's the difference between these two? This is in the system, this is in the control volume. Well, the system is kind of is usually a defined mass of something. And so, but the difference is the control volume, stuff can come and go from it. Okay? So that's what this last term is going to have to deal with. It's going to have to deal with the fact that stuff can enter and leave a control volume. Okay, so what we're going to do here is we're going to do like we just did, but I'm just going to look at this term over here. I'm going to erase all this nonsense because I don't want to look at it. Okay, because it's in my way. We're going to kind of discuss this in the same way. Okay, so let's start with, I guess we'll do this in blue again. Okay, so this is, let's suppose this is salt per volume. Okay, and I'm going to multiply it times rho. So that's going to be, excuse me, that's salt per mass, sorry. Salt per mass. We're going to multiply times rho, which is density, so that's mass per volume. So now I've got salt per volume of whatever this might be. Okay, and now, so I got salt per volume, but now I'm going to multiply it by this. What is V dot dA? Okay, and if you remember correctly, that's Q, so that's the volumetric flow rate. So that's volume per time. Okay, so this is Q. Okay, so that's basically how much flow is crossing into or out of our control volume. Okay, so if we do that, then I've got salt per time. Okay, and this is the salt that's being carried by the Q across the control surface. Okay, so basically if this is our control volume, okay, and for whatever reason Q is coming in, and that Q is, as it comes in, is bringing salt, then it's going to cause the total amount of salt to increase in the system. Conversely, of course, if Q were leaving, it would cause a certain amount of salt to leave. Okay, so that's the idea here. Okay, so let's see. So we're going to go over here, and we'll go back to my red, and I'm going to go like this, and I'm going to say that this term is the rate at which B flows over the control surface. Okay, and this really means out of control volume. And the reason I say out of is because if it had a negative sign, it would be into it. That's just the way this particular sign convention works. So the nice thing about this is, there are some very obvious simplifications here, for example. For a conserved substance, substances, okay, things that don't decay, okay, okay, so in this class, mass and mass and energy and momentum and things like these things are conserved. But like if we were talking about heat or something, well, actually you could probably do this with heat. You would just have a lot of energy leaving through things like this. But this probably wouldn't work because some heat radiates off, and we can't account for that with this equation. But in this case, dB cis dt equals 0. Okay, so that means for a conserved substance, like if it's mass, well, the mass of the system is not changing. Okay, if let's see, if it's steady, for steady flow, okay, then what that means is that what's in the control volume is not changing. So this term goes to 0. So d by dt of the integral over the control volume of b rho dv, okay, that equals 0. Okay, and then the last thing we'll say is that for constant velocity profile. Okay, so in that case, basically, you see we've got this V dot dA up here. Okay, and this is ugly. We don't really like doing that. Okay, but basically if the profile is, like, let's suppose here's our control surface. Okay, and we've got two options, right? The Q can come in and it could look like this, where the flow is fastest in the middle of the pipe. Or we can have the flow coming in like this, and it's constant velocity profile, right? So it's constant in the lateral direction. So if that happens, if we have a constant velocity profile, okay, so that's like a 1D velocity profile. Woo, with V equals V bar, okay, where the velocity equals the V average, then this integral over the control surface of B rho V dot dA becomes much easier. Basically, we're going to sum over all the places where there's Q across the control surface of B rho V dot A. Okay. Now, ultimately, I'm going to do this a lot simpler in general, but let's talk about this for mass. I'm going to kind of do this where we can still see the original, but we're going to do this for mass. Okay, so if B equals mass, okay, then lowercase b is mass per unit mass. Well, what's mass per unit mass? Well, mass per unit mass is just the number 1. Okay, so that's going to make this whole thing a lot simpler. Okay? The other thing about this is that mass is conserved. So if mass is conserved, then this first term is going to go away. So I'm going to be left with 0 equals d by dt, integral over the control volume of that little lowercase b becomes a 1. So rho dv plus over the control surface, that lowercase b becomes a 1, rho v dot dA. All right. Okay, so if we rearrange this, and I will, we'll say d by dt, integral over the control volume of rho dv equals negative over the control surface, rho v dot dA. All right, so that's the continuity equation. Continuity equation. I don't know why they call it the continuity equation. I'm going to call it that all semester because that's just the way it is. But the continuity equation is conservation of mass. They call it continuity equation for reasons that will remain strange to me. If you can tell me why they called it that, I would appreciate it. Okay, so again, we can think about this as, okay, here's the mass per unit volume. We're going to multiply that times a little tiny volume. Okay, so if we take the mass per volume and multiply it by what's in that tiny little volume, and that's going to tell us how much mass is in this tiny little volume. And if I integrate that over the entire control volume, then I'll have how much mass is in the entire control volume. This is how much mass is in the entire control volume. And then if I take that d by dt, I end up with the rate at which mass accumulates in the control volume. Cool. Okay, now if I go over here, okay, so I've got mass per volume, and I'm multiplying it by the flow rate. Okay, so this is mass per volume, and I'm multiplying it by the volume per time that's crossing the control surface. So basically, I've got mass per time that's crossing the control surface. So this is the rate at which mass leaves control volume. Or crosses the control surface, depending on how you want to put that. All right, so that's a lot of mess, okay? And this is one way to do it. And if you look at my old notes, you'll see that I did this a lot. Okay, now I want to do this a different way. Okay, so I'm never going to use this. Okay, but on the old homeworks on Moodle, I did use this. Okay, so don't be too confused if you did this. Okay, what I prefer instead, generally speaking, is this whole thing right here. So we're summing every time something crosses the control surface. So what we're going to do, what I prefer to do is it's got a little negative sign out in front of here. And I want to think about this as, well, okay, let's do this side first. Okay, if we do this side first, the rate at which mass accumulates in a CV, okay, in a control volume. That's the accumulation in the control volume, equals. Okay, now we've got a negative sign. Okay, this is the negative sign. Okay, and now this V dot dA, if we use the kind of, like if this is our control volume, the dAs are out. Okay, and let's suppose the volume's going in like this from right to left. Okay, so then this side right here, this is an in, and the V dot A, since they're in opposite direction, has a negative sign to it. And the out has the V and the A have the same sign, so this becomes a positive. The outs have a positive sign. Okay, so this becomes negative out, which has a positive sign, minus in. Okay, so let's rearrange this, and I like to think about this as in equals out plus accumulation. Okay, and the reason I like to think about this is because it works for almost everything if you just define a control volume. Okay, so all I did was rearrange that equation. Wait, I think I did. Yeah, in is by itself. Out gets moved to the other side, made positive. Doing this, you never have to ask yourself about any of these silly, like any of this. You never have to do this and start thinking about, you know, whether or not the dA has a direction and what its direction is relative to the V. Okay, what we're just going to think about is we're going to think about whether or not stuff, you know, by putting something here, we've taken care of its sign. Okay, if something's going in, it's positive on the inside. I mean, it's positive and it counts for the in. If something's going out, it's positive right here. Okay, if something is accumulating, it's positive right here. If it is getting less, it is negative right there. Okay, so let me give you an example of how I would solve using this. All right, so if I had some kind of pipe here, steady, incompressible flow, and the pipe is flowing in the right side, the left side at V1, and it's flowing out the pipe at the second location at V2. Okay, so I'm just going to go ahead and I'm going to say, okay, well, I want an expression relating these velocities to each other. Okay, so in equals out plus accumulation. Okay, so this only works on a control volume, so we need to define a control volume. So I'm going to go ahead and define one. Here you go. Here's my control volume. Cool. All right, now, in equals out plus accumulation. Okay, here's in right here. Okay, so now we have to think about something that is conserved. Well, mass is conserved. How much mass is coming in there? Well, let's see. Mass, we've got a density at 0.1. Okay. The density times the flow rate. Okay, so the flow rate, Q1. Okay, so if that's not clear to you, we will back up and we will think about this. So the density is the mass per volume, and the flow rate is the volume per time going into this thing. Okay? And so that gives us mass per time that's going in. Okay, so we can do this all with rates, or if you prefer and you want to think about it as total mass, you can multiply it by a time step. So times time, and that'll give us the total amount that's in there. Okay, we'll multiply by time. Okay, cool. All right, mass is conserved, so we can do that. Okay, so how much is leaving? Well, the term's going to look almost exactly the same. Rho 2, Q2, okay, the flow rate 2, and then times that time. Okay, how much is accumulating in this pipe? Okay, in this control volume? Well, it's full, okay, and it's steady. So if it's steady and it's full and it's incompressible, well, the same amount that's in that pipe at the beginning is going to be in that pipe later. So this thing is 0 plus 0. Okay, by the way, accumulation will not always be 0. So get your hopes up. All right, so now we're pretty much in good shape. Okay, because the delta T is the same for both sides, so that goes away when we do some algebra. We said that this is incompressible. So if it's incompressible, then that means row 1 equals row 2, which means I can go down here and I can say, oh, look, well, row 1 equals row 2. So these are algebraically the same, so they can cancel. So I'm left with Q1 equals Q2, okay? And since I didn't give you a velocity profile for 1 or 2, we're going to assume that V1 and V2 are just the average velocities. So we'll say V1A1 equals V2A2. And let's just solve for V1. And we'll say V1 equals V2 times A2 over A1. So what does that mean? Okay, that means if the second area here, if this area is small relative to A1, okay, so then A2 over A1 is less than 1, then V2, wait, is that right? A2 is small relative to A1, then V2 is, then V1 is going to be smaller than V2, okay, because then that means that, let's suppose this number is a half, right? Let's suppose A2 is half as big as A1. Then that means V1 will be half of V2, okay? Just as, you know, whatever, just making it up, okay? So this is a made-up number, okay? So basically, the velocities are proportional or they're inversely proportional as a function of the areas, okay, or something like that. Okay, so let's see, we're at 21 minutes. Do I want to do another example? Let's do one more example, and then we'll do a little station identification break. Okay, come on, punk. Pause. All right, so let's go up here to this example. Okay, so we're filling a tank. Okay, and so for whatever reason, we decided to fill the tank by, instead of putting the hose into the top here, we decided that we wanted to have a pipe at the bottom moving the water in down here. Okay, so we want an expression that's going to describe how that tank is filling. Okay, so in equals out plus accumulation. We recognize immediately this is a mass conservation problem. Mass is conserved. So what do we have coming into this sucker? Okay, well, in, let's see. Okay, well, this is almost always the same thing. We want mass flowing in. It's going to be rho at 1, the density at 1, times the flow rate at 1. Okay, so that's the mass per time flowing in. Now I could do this as a delta T. I could leave the delta T out. I'll do this both ways to kind of give you an idea. Okay, that's how much is flowing in at position 1. What about out? How much is leaving? Well, I don't know. Let's see. What's our control volume? Well, let's see. Here's our control volume. Okay, so I'm going to make the control volume so big that nothing's leaving. Okay, so there is no out if you do it that way. Okay, no out. Okay, what about accumulation in our control volume? Do we have more at time 2 than we do at time 1? Seems like we probably do, right? So how much is in that tank? Well, it's going to be the density that's in the tank. Let's see, let's call that rho capital T for tank, times the volume of the tank. Right, that makes sense, right? Density, T, volume, tank. Okay? So if you do density times volume, you're going to get mass. So basically we've got this much mass coming in, okay, over time T. And we've got, well, really, this is not right, is it? No, I don't think it is. So actually what we've got here is we've got the change, plus the change in mass, right? That's our accumulation. Okay? So this much is coming in. So this is the mass flowing in, mass flow in. And this is the change in mass in the tank. And hopefully this makes sense to you. Like, this seems, logical to me that the amount of mass that flows in, if none of it's leaving, well, that's going to determine how much more mass we have in the tank. Okay? So the first thing I want to do is I want to take these rows, I want to take this row right here and move it outside of that delta because it's incompressible. So rho 1 equals rho T. So those go away. Those are just going to cancel algebraically like that. So I'm left with Q delta T equals delta V T. Okay, volume tank. V tank. Okay. So now what do we want? Okay, well Q is going to be V1 A1. Okay, because it's it's the average velocity. And I'm going to take this delta T and I'm going to divide both sides by it. So I get delta VT over delta time. Okay. So what I want to do next, I'm going to make this a derivative. Come on, man. Okay, I'm going to take the derivative. I'm going to take the limit of both of these as delta T goes to 0. Well, what does that do for me? Well, that makes V1A1 equal dVT dt. Okay, and then we could say V1A1 equals, well, what's the volume of a tank? Well, the volume of the tank is the area of the tank. So it's going to be D, the area here. Right, so usually that's going to be pi r squared. But let's just leave it as area of the tank. Area of the tank times h. This is h right here. Okay, dt. And then what we can do is we can rearrange this. And I can say, well, V1 A1 over AT equals dH dt. Okay, so the rate at which the surface of the water goes up is a function of the difference in these two areas, or the ratio of those two areas, and the velocity at which the water comes in. And this should make some sense to you. Now note that this is almost the exact same answer we got over here. Right? It's almost the same. In fact, I would argue with you that it is the same. Okay, because I'm going to show you another way to do this. Okay, so first thing I'm going to do here is I'm going to do in equals out plus accumulation. So in this case, what I'm going to do is I'm going to draw this slightly differently. So what I'm going to do is I'm going to erase this control volume. If it will let me. It really hates erasing. Okay, and I'm going to redraw the control volume somewhere slightly below the surface. Okay, so now at a later time, the water has moved from this point to now it's here. Let's imagine, right? And at a time after that, the water is up here. Okay, so what's the difference there? Well, the difference now is I have water leaving the control volume. So this water is no longer in the control volume. It has left. So N is rho 1, Q1. Okay, so that's the rate that it's flowing in. I'm going to leave it as a rate. Equals out. I'm not going to put the delta T there. Okay, out. Well, what's flowing out? Well, rho 2, Q2. Right? Okay, because now that is leaving the control volume. Okay, and then plus accumulation. Well, in this version, the amount that's in the control volume has not changed. Okay, so this becomes a 0. Okay, the rho 1 and the rho 2, these two are the same. I mean, these two are going away, okay, because they're the same value. So I get V1A1 equals Q2. Well, I get V2A2. Okay, but in this case, right, A2 is the area of the tank, and the velocity 2 refers to the velocity that the water surface is rising. Well, what do we call that? Well, we call that the change in the height with respect to time equals V1A1. Okay, and if we rearrange that, we're going to get dH dt equals V1 times A1 over AT. Okay, so that's just another way to do it. Okay, so there's two ways to draw your control volume, which will both give you the same solution. Okay, there's probably other ways. Well, there probably aren't other ways. This problem's fairly straightforward, but whatever. All right, so in part 2 of this, I'm just going to keep on working continuity. Okay, solve problems using continuity, understand this control volume approach. That's what we're doing here. Okay, I'm not super concerned about the Reynolds transport theorem. If you go really into more sophisticated fluid mechanics, that might become important. But to me, it just muddies up the works. Okay, so we're going to focus on continuity and control volumes. Okay, so that's it, and I'll be bringing you B shortly.